From Neural Newscast, this is Model Behavior, AI-focused news and analysis on the models shaping our world.
I'm Nina Park, and you are listening to Model Behavior. Today, we are taking a closer look at a significant release from Meta AI research called DINOv3. This is a substantial scale-up in self-supervised learning that attempts to solve a persistent technical issue in computer vision: how to grow a model's parameter count without losing its ability to perceive fine local details. Thatcher, this is more than just a standard version update for the DINO framework.
It definitely is, Nina. Meta AI research, working alongside teams from Inria and WRI, has pushed the DINO architecture into the 7 billion parameter range. For context, most vision models used for these specific tasks are much smaller in scale. What is most interesting here is how they address the scaling paradox. Generally, as vision transformers get larger and train longer, they improve at global tasks, like identifying an object in a frame, but they actually start to degrade at local tasks, like pixel-level segmentation.
The research notes that feature maps often become noisy, or what they call a collapse at these higher scales, making precision difficult. How did the team manage to maintain that local consistency while still reaching a 7 billion parameter count?
The breakthrough they introduced is a technique called gram anchoring. In the self-supervised learning process, you have a student model learning from a teacher. As the student model scales up, the relationships between pixels can get messy. Gram anchoring essentially forces the student's internal feature relationships to anchor to a purer state, often derived from high-resolution inputs. It basically provides a high-definition reference that keeps the model's internal vision sharp, preventing that noisy feature drift that usually kills performance on dense prediction tasks.
And the data required to train a model of this size is massive. They didn't just use standard labeled sets like ImageNet. They actually built a massive new dataset specifically for this project, called LVD1689M.
Right. They started with a staggering 17 billion images from the web and used a hierarchical filtering process to narrow that down to about 1.7 billion high-quality samples. They also integrated several architectural features we usually see in large language models, like Rotary positional embeddings and SwiGLU activation functions. This allowed them to use a constant learning rate schedule throughout training, meaning the model could undergo much longer training cycles without plateauing or losing its edge on dense prediction tasks.
Thatcher, let's talk about the practical side of this release for the community. The report says DINOv3 performs exceptionally well on dense tasks without any fine-tuning. For developers and researchers, that seems like a significant efficiency gain.
It is a major win, Nina. On benchmarks like ADE20K for semantic segmentation, DINOv3 is outperforming dedicated models that were fully fine-tuned for those specific jobs, even though DINOv3 is being used as a frozen backbone. This makes it an incredibly powerful engine for open-source frameworks like ProxyCLIP. Since DINOv3 provides such clean spatial priors, it can effectively guide other models that understand semantics but struggle with precise object boundaries.
I was also interested in the cross-domain capabilities mentioned in the paper. Specifically, I noticed how it handled aerial and satellite imagery quite well, despite not being specifically trained for those perspectives.
The visualizations in the paper are quite striking, Nina. Even from a satellite view, the model can distinctly separate roads, buildings, and vegetation. It shows that by solving the scaling paradox, they've created a model that captures the underlying geometric and semantic structure of the world. It's a very robust representation that doesn't just rely on seeing the same types of photos over and over again.
It certainly positions Meta to continue leading in foundational vision research. Thank you for the deep dive into the technical details, Thatcher. Thank you for listening to Model Behavior, a Neural Newscast editorial segment. Visit mb.neuralnewscast.com. Neural Newscast is AI-assisted, human-reviewed. View our AI transparency policy at neuralnewscast.com.
This has been Model Behavior on Neural Newscast, examining the systems behind the story